Okay, yes, welcome. First of all, thanks for the invitation again, second time for me. I decided to talk about data collection for high-resolution subtomogram averaging. And thinking about that, I first had to go back a bit because it's not something that I've been working on just for the last years. It's, I was hoping this would work. Ah, I got my own one and it still has a problem. Ah, okay, here we go. So, this is a Polara. It's one I built myself. It was shipped to Sriram Subramaniam in 2002 or 3, I think, when I was working in the FEI factory building these things. We also had to install them. And one of the things that happened in these years is that this new thing came up, automated tomography. And that's where I first got in contact with it. So we tested these things in the factory. You learned a bit how tomography worked, especially the tomography 3, the dreadful blue version. And that's when I first got in contact with it. The plastic bag, by the way, that's just an old factory trick. You put the plastic bag over it, you have fantastic drift performance. It's kind of, you know, they put a Titan in a box, and I said we put a Polara in a bag. Works really nice. I really highly recommend it. But this was Sriram's Polara, and then a few years later, Sriram had a bit of problems with it in 2006, and basically convinced FEI to send somebody over, which was me. So I spent a full year in his lab. I was basically available 24/7 for a full year. They would call me, I would have to be in the lab in 5 minutes to kind of get stuff going. And meanwhile, in that year, we developed at FEI batch tomography. I did this together with Andreas Vogt, who at the time was writing the tomography software. So we just went back and forth. It was just one developer and me. I just told him what I wanted. The next day I got a new version. And that's how we kind of got batch tomography running. And at the time, Sriram was working on this HIV stuff. That's why I needed automated tomography, which was very important. So we had a Polara. I went there, had all the support that you know, that people could have at the time. And then this thing is totally not working. Good. And then got a disaster struck, because then suddenly there was a paper from Florida State University. The microscopist was Leeuw. And they basically, yeah, more or less got a structure on a CM300 VEC with a Tietz camera, 32 angstrom resolution. Then got even worse, because then Steve Fuller and Julia Zanetti and John Briggs also had something. They had different structures, by the way, but that was a different story. That was also on a CM300 with a GIF 2002 2K CCD, 28 angstroms. And then, so that first paper, Leeuw did the microscopy. Then somehow, I don't know why, June ended up with Sriram, and then 2 years later, they then also got this structure. One of the key things, and that's why I'm pointing this out, is that we decided already in 2006 to drop to 200 kV, because it's on a CCD. CCD has a better performance at lower kV. Crucial thing, and that's why I quickly wanted to show this. Then fast forward, I left FEI in 2011, I think. I went to EMBL. John Briggs had some interesting projects. This was one of them from Tanmay Bhagat, who was somehow working on same kind of stuff, not the glycoprotein, but a different layer. And at the time, because you know, these are samples that you can't solve by a single particle, every particle has a different size, and Tanmay made tubes out of them. And so we took film images, high-dose film images of the tubes, then went to the darkroom, develop everything, get the negatives, back to the microscope, have the light thing, put the negatives on, go back to the position, set up a tomogram for each position, then take tomograms, then do subtomogram averaging of the lattice, basically of the tube, which then gives helical parameters per tube, because every tube had different helical parameters. And then do real space helical reconstruction and average it. And again, so this was film, there were no direct detectors at the time, and the tomography was done on a GIF 2002. Then Tanmay left, Florian took over. I mentioned, you know, years ago we dropped this thing to 200 kV, let's do that. So we dropped to 200 kV, we're still on a GIF 2002. This is done with FEI tomography at the time, so we went from 0 to 45 and then 0 to minus 60. And we got an 8.5 angstrom structure out of it, which at the time was a thing. Then we got the first direct detector and decided, okay, we want to try it. It was a Falcon 2. So there was a paper where there were two structures, and we used both these combinations. So we used GIF at 200 kV and Falcon 2 at 300 kV. And you basically got more or less the same result. So an energy filter definitely helps, but here, the direct detector without the energy filter was the same as the CCD with an energy filter at 200 kV. And then finally, we got our Quantum K2 because we were thinking we would get scooped left and right by the people that already had these cameras. And that was kind of the time when I had to switch to serial-EM. I was still using FEI software. I'd worked there for 11 years. But as it goes nowadays, if you get a new camera, you have to get serial-EM because the manufacturers will not come up with any software that works. So I've already kind of developed this dosimetric tilt scheme. There wasn't really a question for it. It was just something I came up with myself. I forgot this slide first. This is something we did last year. Somebody was screening, Martin Ober, who did a lot of the sample prep for Florian's previous work. He's now with Florian in Vienna. And he actually put this HIV stuff also on our Thales Arctica with the Falcon 3, linear mode, no energy filter. I was still able to get a decent resolution. So you don't necessarily need the fancy filters and the direct detectors and stuff. You can do this with a ton of microscopes. Because if I can do this on a Thales, I can also do this on a Glacios. I don't see any difference. Software. So I started using in the beginning FEI software, FEI Tomo, which was based on the things that Bram Koster developed in 2001 or 2, I think, where they did pre-calibration and tracking. So you take a tilt series, you measure the shifts, and that's what you apply. That's somehow something that surfaced recently again, but it's a very old idea. At the same time, there was full prediction by UCSF tomography that just say, I just start to tilt and measure the shifts, and I just fit it to a perfect rigid body rotation, which worked really nice for Agar because he had really nice stages. David Mastronada, serial-EM, however, David is the absolute master of getting the worst microscopes with the worst stages and the worst alignments still to collect the tomogram. That's really pretty amazing from serial-EM. So he noticed, like, okay, most of the systems I work with, the stages aren't that great, and this whole perfect rigid body rotation stuff doesn't work. And this prediction stuff, this pre-calibration stuff also doesn't work. So he came up with prediction and tracking, which is really nice. At Florida State, I did some application support at the time. I noticed that Scott Stagg had this UCSF tomography. It's also integrated into Legidon. The nice thing there is the shift curves are stored in the database and averaged, which I still found a fantastic idea. It's just that I've never got myself to install Legidon. But it's still something in my mind that they say you build up a database of shifts over time as you do tilts. It's stored per magnification. Very interesting principle. There was also Tom Toolbox from Martensried, but that looked like you need a pilot license to operate. It was even worse than serial-EM, I would say. And there's Gatan Latitude, which I never got to work. We do this high resolution subtomography at very high magnifications, so small pixel sizes. And just kind of to show, this is an experiment I did a while ago with some apoferritin. You just use one square, set up 3 groups of positions, shoot some apoferritin, plot the B factors, and then it's very obvious that you go higher in mag, you have a better DQE, you get to higher resolution much faster. It's just a repeat of an experiment that Scott Stagg published, I think, in 2006. So high mag means small field of view. This is typical the field of view that we have for most of the stuff that we did in the BRICS group. And in the end, the gold concentration is kind of tricky to control. You need to really up it, and then still, you want to have at least 3 beats in a tilt series to be able to correct shifts and rotation. So that's why you have to go to high mag. High mag means you don't want to lose too much field of view. So you have to be accurate in your tracking. Tilt schemes. The oldest tilt scheme was basically you just go to a high tilt and you kind of sweep it to the other side. Then when the Cryo-Tomo landed with the FEI tomography software, and also the guys in Martensried, several people basically found out it's easier if you start at 0. You start at 0, go up, then go back to 0 and to the other half. But then you kind of get problems when you have to connect the 2 branches. And that's where then in the end I said, okay, let's try if I can just get away with scripting a dosimetric tilt scheme together. Again, nobody asked for it. It was just that Oliver Schreider at the time was working on this influenza stuff. These are low mag images that the FEI Tomo software would save. So it would take a low mag image, we go to high mag, we do the first branch, and we only went up to 45 degrees, 20 electrons dose. You come back to 0, and then you do the other side. That movement is after 20 electrons, square angstrom dose. After that first branch from 0 to 45. It didn't happen everywhere, but in a lot of places on this particular sample. And what you then get is, as you kind of want to connect these two branches, it's not just this shift, there's going to be an X tilt. With fiducials you can kind of solve for it, but somehow all the tomograms that had this effect, you could align and align and align, the residuals were just so high that it was just, in the end you just had to throw them out. It's kind of like, the bad lamella, you see this, throw it out. But at the time I said, okay, well, wait, what if I do a dosimetric tilt scheme? Maybe we can counter this. And it helped with a lot of cases. When it was published, we never did a proper test. We had good results, we had high resolution, and then, some people at them will say, you never argue with success. But then recently, Beata started doing some tests, and this is something that we now have in review, where we took this same HIV sample, it's more or less, the apoferritin of tomography, I would say, and used a couple of different tilt schemes, continuous tilt scheme, bidirectional dosimetric. We did a dosimetric with a decreasing tilt angle and with an increasing tilt angle to see if around 0, if we would over or undersample, if it would be any difference. And we did this with Volta faceplate in focus and Volta faceplate with a bit of defocus. And somehow dosimetry just comes out best. We've tried this very, very rigorous. Again, there's a preprint online about this, and I think we just sent back the reactions to the reviewers. So that's why it's now pretty much become the default at EMBL. Okay, high mag tracking is important. I don't want to lose too much field of view. And a lot of people then perceive this as you need a perfect stage to do this. So these are the movement specs of a standard stage that was developed in the 80s. So it was in the CM, on the Technics, and also on the early Titans. XY movement, if you do a tomogram plus minus 70 is 2 microns. The Z movement, the focus difference is 4 microns. And the reproducibility 400 nanometers, meaning I take 3 holder calibrations, or I do 3 tilt series. The shifts should be within 400 nanometers. That was the spec for the pre-calibration setup. Then luckily we got this single axis Titan stage, and they kind of made the shifts a bit smaller. So it's 1 micron now, 3 microns in Z. Reproducibility is somehow not specified. That's probably because nobody's doing this pre-calibration anyway. The only difference between the dual axis and the single axis is that this dual axis had to do a flip-flop, so it's 2 halves. There's 2 parts, and then the single tilt, this is just 1 part, so it's much more rigid and stiff, and that makes that it behaves better. This is how it actually looks like in the microscope. So these are braids, these are just little tiny wires. Luckily long enough, but still if you go to 70 degrees, there can be some pull on these wires, which is often problematic. When we take tomograms, we often assume, we hope to have a rigid body rotation because we kind of assume the grid to be flat, but if you tilt to a high angle, most of these grids that we look at, just the carbon grids especially, they're everything but flat. We probably could have used molybdenum grids. It's a bit easier then because the molybdenum shrinks just as much as the carbon. But on the normal grids, it's just terrible. Gold grids are so far too thick anyway, because at high tilt you just can't get through anymore. So if we then set up, want to take a tomogram and we want to use low dose, there's another problem then. We want to image this area, we want to focus and track here. This blue line is the tilt axis. On the microscope, the tilt axis will never be exactly on the optical axis, so you need to compensate for that. So in FEI tomo it's called optimized position, and serialia is called tilt axis offset. The problem is, if your tilt axis is not super duper calibrated, then your focus and tracking area would basically have a different, they call it N0 here in this paper. So, they should be in one line, and if this line is not calibrated properly, I'm a little bit off, and I then start to tilt, they have a completely different behavior. Not just from the shift, but also it's cryo, so they probably also have a height difference, and then these things become completely crazy. So it's very difficult to track these things. You have to be very careful with that. So there's all these nice specs about single tilt holders. These are all the shifts from a data set I took for Tanmay Bhagat at EMBL with the single tilt holder, 180 tilt series. And then this is kind of what you get. It doesn't even come close to any of the specs because, you know, these numbers here, these were the specs when I accepted the instrument. So I can get these specs in a very nice controlled experiment. I go to one spot only, don't change anything. You check it a couple of times, looks great. If you go over the entire grid with a real experiment, with a cryo grid that is wobbly and cold and everything, all bets are off. But it doesn't matter because I can just track everything properly and then you get everything in check. To track really properly, first thing you have to realize is the mechanical design of the stage makes that if I tilt, you will see a Y movement. So I'm tilting here, you watch the tilt here, alpha. It increases, and then watch the Y value. 100 nanometers, 170 nanometers, 170. And this is a real movement. So then we go back to minus 70, gets even worse. 300, 600, 700. And this is real. So what you do then in software is you basically say, no, I want to go to these 4 positions. You want to basically reset this Y value when the tilt is done. So here I have 500. But it's there, you just set it back to 0. So you do that, you minimize your shifts tremendously. This has been in the tomography software at FEI for years. And in my script, I also built it in a few years ago. And then recently, David also put it into the serial EM stuff. So it's very important to bring your total shifts back. Another thing I do with dosimetric is you tilt to one side. If you go to the other side, I do a tilt backlash. So, you know, you do 0, you do 3. Then you say minus 6, minus 3, then take an image. Minus 9, minus 6, then take an image. So you always tilt from the same side. Because that's basically a worm gear driving a tooth wheel that does the tilt. And there's always going to be some mechanical backlash. You can see it on your stage. If you go to your stage and you just take the lower part, the Z part, you kind of wiggle it a bit, you will notice there's some space there. So I want to make sure that my 3-degree tilt step is really a 3-degree tilt step, so I always approach it from the other side, and then I know for sure that's not a problem. So I came, in the end, then the script became, I tilt to somewhere with backlash from one side, so I always approach the tilt from the same side. We reset the stage XY, so we say we were here, XY, we tilt, okay, Y went off a little bit, put it back. That minimizes shifts. Then we wait, and we measure drift. For drift, I then say 1 pixel per frame drift. I allow maximum. That's just stage drift. You know you're going to get more drift afterwards from the beam-induced movement, but at least want to make sure that the stage itself is not a problem. So you wait and measure. Then we focus to at least to have the last focus change be less than 100 nanometers. We acquire an image. We align that image against the previous acquired image, and we take a new track reference. Takes a lot of time. Works really well. This focusing to less than 100 nanometers change, I do because there's hysteresis on the lenses, the magnetic lenses, the objective lens. It depends from where you go on the lens with the lens current to a value. It depends what lens strength you have. This is a hysteresis loop, and typically, you know, if you normalize lenses, for instance, what the microscope will do is always go to minimum, go to maximum, then go back to the value you have, so you have the maximum field with the amount of current you put on it. But this poses a problem if you start to change the focus. So here, don't watch the numbers here left, but here I just step focus up, down, and here I plot the relative focus step that I measured with a focus step of 100 nanometers, 250 nanometers, 500, and 1 micron. This first line is flat because I came from a normalization. Then here you reverse, and then you see that the first steps are about 85% of the actual change I wanted, because I'm still on this hysteresis loop. And then after some time, it kind of gets back there. I reverse direction again, you have the same thing. So you either keep track of, I have this focus, I need to go to here, or I need to go to there, and then, you know. You could say, I normalize it, but if you're going to normalize the objective lens every time you do this, then all bets are off. The stuff is just not stable enough for that. So that's why we autofocus iteratively to say the last change should be less than 100 nanometers, and then I know I'm pretty fine with accurate defocus. The 1 pixel drift per frame We are very conservative with 4 electrons per pixel per second, typically on a K2. We want about 3.5 electrons per square angstrom. Then you get these kind of dose rates, these kind of exposure times. We typically do 10 or 20 frames. And then this is the amount of drift that, it should be lower than this to have less than a pixel per frame per second. Very conservative again, but I think there's a reason for it, because here I just plotted a couple of damping curves. The green one is the spatial coherence damping curve. We have so much coherence, it's not a problem in cryo. The red one is temporal coherence. And this one is 1, 2, or 3 pixels drift in a frame. Now, it's only going to be the early frames, but still, I want the stage drift to be low enough that I only have to deal with the beam-induced movement and not any background stage drift. So that's why we always do the drift measurement. Now we got a K3, but then, the dose rate changes, these times change, and then I look at these numbers and it's like, okay, the first thing I'm going to do tomorrow, because I have the cryos booked, is take the drift measurement out. It's just not needed on a K3. So faster cameras help for sure. So that's what I'm going to do tomorrow. This wait time is out, the drift is going to go out. The rest stays in so far until I am absolutely sure that, everything runs properly. And then we can see what else we can skip. So, for serialia calibrations for this dosimetric tilt scheme, pixel size is important. That one, absolute tilt axis, to be absolutely on the tilt axis, that I track and focus absolutely on the tilt axis. Very important. We autofocus in a wide strip. So you basically have your tilt like this, and then we autofocus in this direction. Not in this direction, because that's a tilted grid. It has a focus ramp. And I use the white half strip in serialia, and you just get a bit more accurate focus measurements. Then what's important is, because we do these things, I calibrate the tilt axis. So in the processing, I always tell people, just use the tilt axis angle in the MDoc file, because I calibrated it. The magnification is 1, because we have a Krios with a parallel beam. The tilt angles are fixed, because I've backlashed it. I know for sure that it's 3 degrees every time, so we don't have to solve for these things. It's very controversial, but this is what we've been doing for years. That's all nice with the script. What's now coming up, I started testing it recently, is the dosimetric tilt scheme has been implemented in serialia. You have to click this checkbox first, otherwise this one is not available. It's David, so I always say David implements something, and you get it with an extra touch of David. So, wait. So the nice thing is you can set up groups. So you can say I start with groups of 2, 3, 4, 5. You can do all kinds of things. It has drift measurements built in. Looks fantastic. I'm still testing it, so that's why we're not using it with everything yet. Once you start to use these things, like the tilt scheme from script and also from the controller, there's this XY restore thing. I put it in the script. If you use the controller, there's a property for that. This is also important if you set eucentric height, because that suffers from the same thing. I tilt, Y changes, I need to reset it to get a really accurate thing. And the first test I did with this, because it's fairly recently implemented, is that I see a height difference of about 200 nanometers if I have this on or off. And I need realign item min margin needed to align to a low dose view image, because at Highmags, to realign the item, we in the end up with a view image, a low dose. You center something, you take a preview image, you center it more accurate, you save it, take another view image, and you save it also as a map, as an anchor map. If you then later run a realign the item on this preview map, it will first go to view, center it, then go to Highmag, center it more accurately, which is absolutely needed. Otherwise you don't get the precision of locating everything and getting every single gold bead in your image. Time-wise, when I started with Florian, we needed 1.5 hours for 30-something images. Then with script, we were somewhere between half and 1 hour. With K3, we're currently with script at 25 minutes. And recently, Julia Mohammed, and she used a bit more tilts, is at 17 minutes with the tilt controller. So that looks good. The most important thing is, there's these parameters. Image shift, field of view. I don't want to lose field of view. I still am worried about this drift specification, and I want accuracy focus. But I should adjust those by tilt and by dose filtering. And by dose filtering, I mean, this is what happens if you dose filter one of these stacks. It's very heavy. It's a lot of people don't understand it. The subtomogram averaging really means in the middle you have a couple of Fourier slices with high resolution information, and everything around it is low resolution alignment information. There's no resolution in this whole space. So this dose filtering is so heavy where I then say, okay, I'm losing so much here, I probably don't care about a pixel drift there because I'm filtering so heavily anyway. And that I think is where we can still save time by coupling these things back and say, how conservative do I need to be compared to how much we dose filter anyway when we process this stuff. So, we offer dosimetric as a service through Inex. I think we're just about to join Instruct. And we also have a direct access scheme, which is paid, but it's a contribution. It's not full cost. And you can find this on the EMBL webpage, services, Cryo-EM service platform. Most of this work, the last 8 years at EMBL was with Florian and Will and Beata, basically the whole Briggs group. I couldn't do anything with serialia without David Mastronard and especially Chen Zhu, who has fantastic help files online. And for the really tomo and stage details, Andreas Voigt and Twan van der Oetelaar, who designs, he's the mechanical designer of the stage, have been very influential. And with that, I'm happy to take questions.
Thank you so much, Wim. For sure you'll need PDF of your presentation because it was too fast for me, maybe.
Yeah, but that's why it's filmed and that's why I knew I could put 40 slides
so much
in
of useful
20
information
minutes.
And we have still 5 minutes for questions, so please start. Oops. May I start then? Do you think there is any sense to focus in 2 areas instead of 1?
Have you seen how non-flat this thing was when you tilt it? I mean, these 2 areas assumes that you have a flat grid or that you have a ramp, which still means it's flat.
So it means we just double error. Yeah?
It's just cost time, it's not needed.
Okay.
You need to have small beams and focus as close as you can to the area that you're requiring, I think.
Okay, thank you.
I still ask you about this small beam. So now how small you can use for the tomography now? I think single particle.
Our beams are, I'd say, 10% larger than the diagonal of the camera. So it's really just about covering the camera.
Just cover.
Yeah.
So it's depending on location, of course, then you will. So you have the.
Yeah, but it's, I'd say 400, 500, 600 nanometers.
So you don't have this kind of fringe probe at the top.
No, we have this fringe-free set up since 2-3 years now.
So
But that didn't make the difference. The early results were all without the fringe-free.
Okay.
Yeah.
Then you have to use a bigger beam.
Slightly bigger beam, yes. Yeah. Yeah.
Okay. Yes.
But I mean, here it's 45 minutes to an hour. You set up overnight. You throw these viruses on a grid. They're everywhere. So you're not too concerned about the beam size. In single particle, it makes a big throughput difference.
Yeah.
Here, not that much,
Yeah,
because you have so much
it's
space
all
to
the
image anyway.
argument.
Although, the moment you go on a lamella and your
Yeah.
space is limited,
Yeah.
you probably want a very small beam so you can target more spots, if you can find them.
Yeah, there's an argument. You want this for because of the tomography people seem to, or maybe don't know how to benefit from this small beam. So
Well, if you use smaller holes, I mean, the closer you focus to the actual area that you record, that you acquire, the more accurate your focusing and your tracking is, for sure.
do you use multi-shot? If you find a cell, one shot, do you do more shot of this cell?
In tomography?
Yeah.
No.
No, you will damage it.
No, I mean, these areas, they tilt, they start to overlap each other.
Yeah, that's you cannot do the multi.
You could do it in a line. We've been thinking about it, to do it along the tilt axis. Yeah? Take 3 here, 3 there. But if you look at the, well, no, I mean, it's the lamella, if the lamella would be looking really nice, you just set up a couple of strips, yeah? But then the first thing we need to get rid of is these big black ice crystals that you find on every single one of them.
Yeah. Okay.
So,
Yeah. Okay. Thank you.
So when you set up a lot of positions on lamella which have a pre-tilt based on what angle you use for milling, how do you actually define it individually for the different lamella on a single grid?
the pre-tilt is the same, right?
Not not necessarily, because sometimes you will with a bit more or less angle depending on how close you are to the edge of the autogrid. So
Okay, well, luckily in my case, people haven't done that yet.
okay.
So we map everything with the pre-tilt, as was already explained, and then you run everything with that one pre-tilt.
So you use
But thanks for the warning, I have to watch for that.
Yeah.
It's going to be the next problem.
There is a workaround for that. So you can actually put it, as you have your navigator, you can just put the pre-tilt as the name of your navigator item goes to. You read it in.
And you put it into the notes and then read it out.
And then you read it out, and then you know how to. You can have different pre-tilt for every position.
If you use the
It's a
tilt,
workaround, it's valuable.
if you use the tilt controller, if you use the tilt controller, you could set it in the tilt controller. It's just a bit more work, but so far so good. The amount of lamella and the quality of it, and then the amount of time it takes to acquire the tomograms and set them up, that's not a bottleneck yet. Unless you want to go home at 5. I go home at 6.
Do you have similar comparisons for grouped and ungrouped?
No. For high resolution stuff, we always used ungrouped. The group thing at the time was more for people that do cellular stuff, because they don't have fiducials, and they don't necessarily need the dosimetry because of the dosimetric, but it just helps them with the patch tracking. Because again, if you do a start at 0 scheme, you get this X tilt, everything is just so deformed that patch tracking is just not going to align things. And for those people, just for lamella, this solution was okay, but it was too conservative because we were doing 3-degree steps for high resolution. They want 1-degree steps, and that's why you then do the groups. But those kind of things are typically done at lower magnifications anyway, where I would absolutely recommend to use the tilt controller and just increase the groups. It's super fast, it's super easy. And with the tilt controller, you have the advantage that you tilt up, stuff gets too dark, and then serialia will terminate that branch, finish the other side until it gets too dark. So now you have the option to just say plus minus 70, and we'll let serialia figure out how far we get per tilt series. So I really hope I can get this running soon. But for the really high resolution, the Highmag stuff, if I go to like a 1 or 1.3 angstrom pixel size, even with the tilt controller, things become tricky. And this fast tomo stuff is absolutely not possible there.
Have you ever tried to track tomography on the gold foils?
Yeah.
Did it work?
No, it was the first guest that came by was somebody from LMB. They have these gold foils, and I said, do you also have other grids? And he luckily said yes. No, it was too thick. It was just too thick. Your focusing and stuff becomes too inaccurate at Highmag and tracking and stuff. I do know that Quantifoil makes thinner versions for certain people. I should think about that. The thinner versions might just do it. But the standard ones, they just get too thick at 40, 50 degrees, I think.
The problem I had was that the gold was changing appearance a lot when you tilt even only 2 degrees. Then it looks completely different, and you actually start getting problems with cross correlations.
Yeah, smaller aperture, smaller objective aperture binning helps a bit. You want that gold ring out.
So that tilt axis calibration you mentioned,
Yeah.
is that the one that comes out of when you do, for example, your eccentric height, where you get this offsets?
No. It's a calibration procedure that's described in serialia. You basically put in a gold film, a carbon film with gold beads. You take a proper tomogram, you put it in iMod, you process it, you get that tilt angle out. And that you have to put back in the properties file as the absolute tilt axis angle for a certain mag. So you have to do this per magnification. And then what I do, because at high mag, there's not that much movement from the beads. So I basically take a tomogram in a 1x4 montage. So I have 4 images along the tilt axis to get a lot of bead movement, to get a decent measurement of this bead movement.
So you basically you never then use these values that also come out of the reducing, feed them back into
No, it's fixed. I'd like to fix as much as I can there and not solve it later.
So I have to apologize, but we have to move to the next speaker, but thank you so much.
You're welcome.
Please.